Okay, so moving on to this problem then. The only difference with this problem is it's not factored. Okay, all the problems that I gave you a little while ago were in a factored form. So what you have to do is you have to factor. All of the problems like this are designed so that they do factor. If they don't factor, then it becomes more of a technology problem. So you would factor out an x to the second on this. The common factor is x to the second. So if you pull that out, you would have x squared times 5 minus x like this. Then the problem's identical to what we worked on. Okay. So again, what you would do for your zeros, the first zero would just come from looking at x squared equals 0. Okay, so that's x equals 0 with a multiplicity of 2, like we learned. Multiplicity of 2 is even, therefore you're going to cross at x equals 0. Okay, and then you have another 0 up here. I guess the other 0 would be 5 minus x equals 0. So that would be x equals 5. It has a multiplicity of 1, so that would tell, hold on, I said something wrong. Did you guys catch what I just said wrong? Guess not. Okay, if you have an even multiplicity, what happens? Touches, okay, right, oops. Okay, the first one has an odd multiplicity, so you cross. So the only difference is factor. If your problem's not in a factored form, you got to put it in a factored form, okay? So we got that. Okay, the Y-intercept, well, if it's in a non-factored form, it's real easy to do this. If you do f of 0 in the original problem, you would get 0. Okay, just plug in and do f of 0. You can work in the original function. So you get a Y-intercept at y equals 0. The degree on this is staring you right in the face. Okay, you don't have to add the multiplicities, but notice the highest power is 3. But if you did add the multiplicities, you get 3 anyway. Okay, the leading coefficient is also staring you in the face on this problem. It's -1. Okay, so that's it. Can you see okay? No. It seems like that light. Do I need to turn that light off? Okay, I turned that off at the beginning of class and then it's like it came back on. That's it. That's what it needs to happen. Okay, can you see better now? I can. Much better. Okay, so I got everything on the problem now. So now we're ready to put together a graph. So once you get all that stuff put together, then it's just a matter of sketching your graph. All right, so let's see what we got here. So we have a 0 at 5. And then we have one at 0. So let's see, I'll put a dot on 5. That one had an odd multiplicity, therefore it's going to cross. And then you had a 0 at 0. It had an even multiplicity, therefore it's going to touch. Okay? Now what happens on this one is it's an odd degree with a leading coefficient. So remember, odd degrees go like this. Okay? The way this one goes, if it's a leading coefficient negative, then the endpoint behavior goes like that. Okay? Then you just kind of sketch it from here. So we got everything that we need. So we just go there. You would have to change directions. Then at some point, you'd have to change directions again like that. So that would be what that graph looks like. Okay? And that's a very accurate graph. It has the main ideas that you want to see in the problem. Okay? Any questions about that? Okay? So the only difference with that is factoring. Some of the problems I give you on homework will be in a factored form. Some of them aren't going to be. That's what makes it a little different. Okay, so let's see. A couple of other simple things we're going to look at. On the next page, a little bit more terminology. So we're going to look at what we call turning points. And a turning point just means it's like a minimum or a maximum. All it means is the graph changed directions, like from decreasing to increasing and so forth. So this example right here has 1, 2, 3 turning points. Okay, so it turns out you can tell at least something about turning points by looking at the degree. All right, so it turns out that it goes like this. The maximum number of turning points is always going to be 1 less than the degree of the polynomial. I'll explain why. Now, that doesn't tell you how many turning points there are. It just says that's the maximum number of turning points. Okay, so let me show you kind of what happens on this then. Let's say that you have a degree of 3, and then I'll do another example where we have a degree of 4. Okay? So here's what would happen. If you had a degree of 3, well, the graph is going to do one of the two endpoint behaviors we've talked about. Let's just assume that it does something like that. Okay? Well, the thing is important on this, if your degree is 3, then it means the maximum number of zeros is 3. Okay, that's a fundamental thing you want to know. If it's degree 3, then it cannot have more than 3 zeros. Okay, it cannot. It doesn't have to have 3, but, or intercepts, I should say, it will have 3 zeros, but some of them might be what we call complex numbers. So here's the idea. Let's just say that you have 3 zeros. Okay, just put 3 zeros somewhere. Okay, and let's just say that we cross through those. So if we went through and crossed like that, now let's see how many turning points we have in this problem. So notice you've got 2 turning points. So 2 turning points is always the maximum turning points is always 1 less than the degree. That's why. Okay, does that make sense? The only way to make sense of that's draw a picture and just kind of see how that works out. Now again, if it's a degree 3, it doesn't mean that it's going to have 3 x-intercepts. It may just have 1, okay, but the most it can have is 3. That's what's important about that. Okay, here's what would happen if you had a degree 4. Okay, well, let's just say that, okay, it's an even, so one possible endpoint behavior would be they turn up like this. Now what this means again is the maximum number, I should say maximum number of x-intercepts is equal to 4. So you can't intercept the x-axis more than 4 times. That's impossible. So let's just put 1, 2, 3, 4 zeros on there. And let's just loop through them however we want to. And what we would have on this time, let's just make some of them touch. So that would go like that maybe. Maybe that goes like that. Maybe that goes like that. All right. Let's see how many turning points we have. So you would end up having a turning point there, there, there. Whoa, hold on, I did something wrong. Yeah, I did something totally wrong. I'm not paying attention to what I'm doing here. I didn't do that right. All right, so let's just say that we have 1, 2, 3, 4 x-intercepts. You have this endpoint behavior like that. I'm just going to loop through them kind of like this. I wasn't drawing through that right. Okay, so let's just say we have something kind of like that and something kind of going like that. Okay, so notice we'd have 1, 2, 3 turning points. Okay, that's the way that goes. All right. Okay, so that's what the idea is. Now will tell you the maximum number of turning points. This is just a real simple kind of idea here. So these are real easy to do. This example here, the degree is 2. Therefore, the maximum number of turning points is 1. Okay, and you should know that. That's a parabola, right? If you graphed this thing on your calculator, you get a parabola opening downwards, so you'd therefore have 1 turning point. Okay, a quadratic function always has 1 turning point, always. Okay, so that's how that goes. Okay, let me ask a question on this one. Do you know what the degree on this one is, just by kind of looking at it in your head? Without multiplying it out, obviously. Any idea?
4.
Not 4.
That's it.
8. I think you were holding up an 8, weren't you? Okay, good. Okay, it comes from here. All you got to do is look at the highest powers of x in each parenthesis. So it's really just x to the 4th times x to the 4th times x to the 1st gives you x to the 9th. So you have a 9th degree polynomial. Okay, all right. So how many turning points maximum? 8. That's the easy part. Okay, well, when you do the degree on that, just think about what would happen if you multiplied the highest powers of x. That's all that matters. Okay, by the same logic, can you tell me what the degree of the next one is? That's 4. Okay, so again, you're just really doing x times x times x times x, which is x to the 4th. All right, so that would end up giving you then 3 turning points like that. Okay, so remember, you're just kind of adding up the highest exponents on each factor will give you the degree. Okay, all right, I don't know if you're going to use that very much. It's just something that they had in the book. It can be useful, I guess, but the main thing is we're trying to learn enough that as a calculus student, you can recognize the function and at least, and pretty quickly in your mind, know what the graph basically looks like. That's the idea. Okay, so let's see. One last thing on the next page. I'm going to do 2 examples of this, and then that'll close off this, and then we'll start into 3-2. All right, so what we're doing on this is if you knew the zeros and you knew the degree, then you could form a possible polynomial. Now, there's an infinite number of possible answers to this problem. There really is. But what we're going to do is just kind of form it like this. So the idea is we're going to put this in a factored form. Since we have 3 zeros, you're going to have 3 factors, okay? So it always kind of goes like this. It's always x minus something. The general structure of your factors is x minus something. Then what you do is just put in your zeros. So if you put in a -1 there, put in a 1 there, put in a 3 there. Now that is a possible polynomial. You could also add multiplicities, but don't do that. Don't make your problem more difficult than it needs to be. Keep it as simple as possible. So what you would have is x plus 1, x minus 1, times x minus 3 like this. Now when you do this on your homework, you're going to be required to multiply it out. I didn't give you anything like to a 10th power or something crazy like that. Just something to the 3rd power, maybe 4th power is the highest that you have to worry about. So yeah, we are going to go ahead and multiply this out. So what I'm going to do is just put together the first 2, FOIL the first 2. Okay, I'm just going to draw a parenthesis, bring down the x minus 3. You can't FOIL all in one step. I see students do that sometimes. You got to pair them up, FOIL, then continue. So when I do the first step, that's going to be x squared. Outside is minus 1x. Inside is plus 1x. You can do this in your head too and bypass this if you feel confident with that. So that would end up giving you x squared minus 1 times x minus 3 because the x's cross out. If you knew that, you could bypass that foiling step. Okay, then what we do is just FOIL again to get our final answer. So what we have is x squared times x is x to the 3rd. X squared times -3 is -3x squared. Inside term, -1 times x is -1x. -1 times -3 is positive 3. So a possible answer to this problem would be x to the 3rd minus 3x squared minus x plus 3. Okay, there's other possibilities too on this problem. In fact, if you change those multiplicities in the first step, then you'd get something different that would still have the same zeros. Okay, but that's the idea, is you can put that together and then multiply that out. Okay, is everybody with me there? Okay, the structure is always x minus what the zero is, x minus. Okay, that's how I'll kind of tell you how to set that up. So on your homework, you probably had one like this, maybe one like this, but I'm not going to overdo it on this. I want to just kind of, it's good practice to multiply stuff out. So this one will have x minus, and this time it looks like we just have 2 zeros. Okay, so the first thing they have is a 0 at -1, and that had a multiplicity of 1, so that means that exponent outside that factor is 1. Then we had a 0 of 3 with a multiplicity of 2, so that's it. Okay, so what you would have is you would have f of x is equal to x plus 1 to the first times x minus 3 to the second. This one's not too hard to multiply out. Again, anything I gave you is not going to be real big long thing that takes up a whole page of paper. Something more like this. Okay, now let's multiply this out. Now here's how I would do this. There's more than one way to do this. I would just work on that part and try to do the shortcut. Just bring down the x plus 1. Okay, so let me go over this shortcut again. I think everybody really needs to get confident in doing these shortcuts if you aren't already. You square the first term, which gives x squared. You square the second term, which is a negative squared, so that is a plus 9. Okay, then what you do is you multiply the two terms together. That's negative 3x, and then you double it to get negative 6x. Okay, do that. Don't do that unless you are totally 100% confident that you know what you're doing. Otherwise, just write it out twice and FOIL. But that's something that's worth knowing for higher math, is how to quickly square stuff in your head. Okay, then we multiply this out. So we would have x times x squared is x to the 3rd. Then we'd have to take x times negative 6x is negative 6x squared. x times 9 is plus 9x. Then you start over again. 1 times x squared is x squared. 1 times negative 6x is negative 6x. And then 1 times 9 is plus 9. Okay, that's multiplying everything out, collecting like terms. So you'd have x to the third. Negative 6x squared plus x squared is negative 5x squared. 9 minus 6 is plus 3x. And then plus 9. Okay? All right, that's the idea. All right, now I'm going to show you something on this one. Just you can do this on your calculator. You can just watch if you want to. Calculators can check you in a lot of situations, so I just want to see if I'm right. Okay, this is kind of a good way to help you make sense of these problems. So I'm going to put in x to the third minus 5x squared, my answer, plus 3x, and then plus 9. And then we'll see if this looks like it has all the features of the problem that I gave you. Okay? All right, so let's see. We had a 0 at negative 1. Look at that. We have a 0 at negative 1. And it crosses. It crosses because the multiplicity was odd. That looks cool. We had a 0 at 3, and it touches. So does that make sense to you? So this has all the features of the problem I gave you. You can tell that it has a 0 at negative 1 crossing, 0 at 3 touching. So it looks right visually. Does that make sense to you? So you can kind of check that. I mean, that doesn't verify that you're right necessarily. But that gives you a real high probability that you're right. Okay? You could still made a little mistake somewhere, but that's what I'd suggest that you do on that then. Okay.